Yeah, thanks. So yesterday we talked about the notion of being dualizable. And we showed that for dualizable categories, we have this resolution C int C omega 1 int of the continuous Kalkin category. So it can be resolved by compactly generated categories. And then we also talked a bit about the category PRL dual. Of dualizable stable infinity categories and strongly left adjoint functors. So it's not a full subcategory of PRL, but I mean it's strongly left adjoint functors, and I guess these are also the internal left adjoints. This is something you can do very generally in two category. You can form this category into a bunch of Latin properties and support some theory of Hochschild homology and so on. And one thing I wanted to mention and didn't mention is that this is actually itself a presentable infinity category. This is a result of Maxime's, and I guess Sasha has included a different perspective on it in his paper. And in particular, it has co-limits and limits. And one nice thing is that the forgetful functor, here a dual, down to cut infinity, to PRL, preserves co-limits. So in some sense, the outcome of that is we do understand co-limits. And let me remind you how to think of co-limits in PRL. The way you think about co-limits in PRL is somehow that the forgetful functor, the cat, doesn't preserve co-limits. What happens instead is PRL is equivalent to PRR op. Right? You sort of take a diagram of left adjoint functors, you just pass to the diagram of right adjoints, and then the forgetful functor down to cat. I guess here now it will go to cat infinity op. Maybe put a hat. Size issues, and then this functor preserves, I guess now co-limits, put the op, so without the op it preserves limits. So the way we compute co-limits in PRL dual is you just take the underlying co-limit in PRL, which means the limit in infinity categories of the adjoint diagram. And it is a very nice exercise to prove this, so maybe I state it as an exercise. Prove this. I mean, prove that this functor preserves limits, co-limits, so in other words, that co-limits are computed underlying. And so here's what you need to use. You want to look at PRLR, category of presentable categories and functors that are both left and right adjoint, because somehow PRL dual is a subcategory of the opposite of that. Right? Because we can just pass to the right adjoint of a given functor, and that again will be left adjoint by definition of being strongly continuous. And you use that co-limits exists in here and are computed underlying.
Do you mean limits?
Do
you mean limits?
Limits exist in here and are computed underlying. Sorry, I want to do a co-limit here, so I pass to here and compute a limit. And then you end up just having to prove that if you take a limit in here, where every object is dualizable, then the limit again is dualizable. And that sort of, in my opinion, is a very, very nice application of AB6. Because if you take a limit in here, then all transition functors preserve limits and co-limits. As a result, in the limiting category, limits and co-limits are just computed pointwise. And then you see immediately if AB6 holds like pointwise, it holds. Right? Because computing stuff just holds. That's, in my opinion, like AB6 is the cleanest way of seeing that immediately.
But you can also prove directly that white hat exists, or J hat.
Alright. So there's a bunch of proofs, but like the statement is true. And I think somehow Sasha will maybe talk about this, but sort of limits are somewhat more opaque in PRL dual, and that's kind of part of like the subtlety of PRL dual, that limits are kind of complicated to understand, and under some additional assumptions you can sometimes understand them. Okay, let me also make two slight corrections. I mean, the first thing I claimed that Chief X was dualizable if X is locally compact, and I claimed that you didn't need Hausdorff, and I think this is false. Like, it's definitely dualizable if X is locally compact Hausdorff, and so, I mean, it's slightly more general, but it's not sufficient to just assume that it's compactly, locally compact.
It's to be separable, right? You also want it to be separable. X.
Separable, you mean?
Like, kind of.
No, it's not necessary.
I think it's.
No, it's not necessary.
I don't think countable is necessary. I think in Joyal Johnston they have a nice characterization, and a version of that goes through for like higher categories. And the second correction I want to make is
Can you write down the first correction, please?
hmm?
Can you write down the first correction?
You,
Oh.
you,
I mean, I only said it orally yesterday, so let me also say the correction only orally. And so I also made a claim that transfinitely compactly exhaustible. I think Johan asked whether it's enough to check that for ordinals, and that's false. You can check it for posets, but not for ordinals. So that's the second correction to what I said yesterday. Okay, so these are the corrections. Sorry, Claudius, but it would take very long to write down. Okay, so, and one thing I did in the end yesterday, let me repeat that as well, was like how to define continuous K-theory. Continuous K-theory of a dualizable category. And the way, I mean, this is due to Sasha, so you can define it as a fiber of the K-theory of this resolution. So you can take K-theory of C omega 1 to K-theory of Kalk's continuous. See? And this is classical K-theory, right? This is a small category, this is a small category. So this is classical non-connective K-theory. It's very important that you use non-connective K-theory, but this is classical algebraic K-theory. And of course, I mean, this has countable sums, as I said yesterday already, so this is kind of, this will vanish, the K-theory of that, by Eilenberg-Swindel, so it's omega of K-theory of continuous type of category. And that's the definition of K-theory. And let me just say, I mean, this is kind of how I got in touch with this whole theory initially when I learned that Sasha had this generalization of K-theory. And I think this is very useful. Let me maybe draw a little picture for that. Like, what is the range of definition of algebraic K-theory? I think somehow, historically, the first thing that was done by Quinn was he defined it for rings. And in fact, I mean, the way he did it is he immediately realized, and so maybe it's not quite correct that these are like not immediately done, but sort of the way he did it, he observed that it actually only depends on the category of projective R modules, right? By some sort of group completion procedure, like, and this is maybe like additive, maybe infinity categories, just additive categories. So that's somehow the generality in which it was defined. And then later, I mean, you can actually generalize this even further to, I guess, I mean, Phil did maybe exact categories, but in order to prove some localization statement, but maybe nowadays we would say stable, small, stable infinity categories. Small. Right, and so the way it works is somehow here, instead of Proj R, you put like then the perfect derived category. So let's let me write mod R omega. Right, so somehow K-theory of R defined here is the same as K-theory of this category, is the same as K-theory of this category. And one of the advantages of having this like stable infinity categories is now you have more categories. For example, if you want to have a scheme and take the quasi-coherent derived category of that scheme, now you can immediately apply K-theory to this, and I mean, this is like sort of, I mean, yeah, I'm not going to say what this exactly is. So it's a correct quasi-coherent, I guess I should sort of prescribe Q code X for a scheme X. And so you can immediately define like algebraic K-theory by means of that.
You mean the compact object K-theory?
Oh yeah, sorry. Thanks. Yes, absolutely. And then somehow, this is kind of a very useful step. And then somehow what Sasha does is like he extends this to this bigger world.
looks like me.
Of dualizable infinity categories. These are big categories, so this guy will become mod R. But one of the advantages is not just that I extend the function, of course the inclusion of like small stable infinity categories in dualizable stable infinity categories is fully faithful. So it doesn't like give me more in this case, but there's a bunch of objects in here that we care about which are not present in one of the smaller clouds. And these are like, for example, we have the category, I guess, this category mod R, I, it's almost categories. Here, right? We have these nuclear categories for some analytic ring R. And we also have these categories of sheaves on a locally compact Hausdorff space. These are, I mean, definitely not compactly generated. So now we can take K-theory of these objects. And I think Sasha will talk about like the result of computation of K-theory of these objects. At least I believe for
almost models I don't have anything smart to say. It's
Rust. But so, you see, this is kind of, in my opinion, one of the reasons we care about this continuous K-theory, because we can define it for objects where we always wanted, in some sense, to understand what its K-theory is now in a very natural way. You just write down a category and apply a functor. That's kind of the big advantage of that.
I guess it is subtlety about idempotent complete.
What is the subtlety?
I mean, idempotent complete, if you're not idempotent complete, maybe it's not recoverable from
Yeah.
information.
Yes. I think, yeah, what he's finding out is it's only fully faithful once I say idempotent complete. That's of course true. Once I pass to int, I lose the distinction between a category and its idempotent completion. Okay, so that's kind of K-theory, and I don't want to say much more about K-theory, but Sasha will, and maybe Dustin. And I want to talk a little bit now about mediatality and fixed functors. What's the situation here like? I have a continuous map between topological spaces. Then what I get is like, I get this classical adjunction. I can pull back a sheaf on X and produce a sheaf on Y. And sheaf, as I use it only for, say, sheaves of spectra always, but sort of, I think pretty much everything works if I do sheaves of chain complexes and stuff like that. And this is kind of, I mean, this functor by definition is the adjoint of the more, like maybe easily defined functor f lower star. This is a junction you always have, and here you definitely don't need like y and x to be locally compact Hausdorff or anything. It just works. And then the thing is, if you have a map which is separated, rated, and locally proper, then you also get this other junction, like you get this lower sheaf functor from sheaves y, sheaves x, f lower 3, and this has a right adjoint f upper star, f upper 3. Thanks. And note that, I mean, I think in many sources you see this like only spelled out for locally compact Hausdorff spaces, and that's because like every continuous map between locally compact Hausdorff spaces is separated and locally proper. But this generality, to my knowledge, was like introduced by Schnürer and Circle. They sort of write down this adjunction for separated locally proper maps. And so, in some sense, if you want, just assume everything is locally compact Hausdorff, then you just get it for every map.
By the way, it's like you can even do it for locally separated.
Oh. I guess it's the same logic, yeah. Okay, maybe not. Okay, so I'm going to say something about it. I'd be interested in like. And I guess, I mean, this is like 4 of my 6 functors, and then on sheaves X, we have Kepler and Pom. So it's the symmetric monoidal category, which is closed. So these are the remaining 2 functors of the 6 functors, and then, I mean, there's a bunch of like relations between these 6 functors that I think most of you have seen versions of. I have like projection formulas, I have like proper pullback style formulas, proper base change formulas, and like, of course, lower shriek and lower star are functorial in Fs, so if you compose 2 morphisms, the shrieks and stars composed in the appropriate way, and the upper star is like a sort of symmetric monoidal functor. So I think recently people have like formalized really nicely what these 6 functor formalisms are, and this is one. And I want to give you like a little bit of a perspective on this 6 functor formalism that I find very pleasant using locally rigid categories. And so let me maybe introduce this notion. So what the upshot is going to be that for a locally compact Hausdorff space, sheaves is going to be locally rigid. And locally rigid is a notion which is stronger than dualizable. it means it's not only dualizable, but it's canonically self-mutual. That's kind of what locally rigid essentially means, right? So because somehow we've talked about categories being dualizable, we haven't really talked so much about the duals, what the duals actually are. And that's what I want to do now. This is kind of this notion, and that's the following definition. And this definition is due to Rankin, Gasbury, Kashtan, Reskin, Rosenblum, and Warshawski. 7 authors. I'm not going to write down the names here, but what's the notion? So C is a commutative algebra in PRL, and it's called locally rigid. You may call it semi-rigid originally, if the following holds. First statement is that the tensor product, which is a functor from C tensor C to C, admits a continuous, co-continuous right adjoint. Right adjoint. Right, so of course, if I say commutative algebra in PRL, then this functor preserves colimits, it admits the right adjoint. So the condition is that the right adjoint itself preserves colimits. So it has a further right adjoint. It's like, this, in other words, this is a strongly continuous functor. So, which is called delta, goes from C to C tensor C. And so the condition is which is a C bimodule map. C bimodule map. What does this mean? Of course, C is a bimodule over itself by multiplying from both sides. And the same I can do here. And the multiplication is pretty much by definition a bimodule map. That means the adjoint is the Lax bimodule map. Right? So somehow if you tensor like from the outside here and then apply the multiplication and do it the other way around, you get a natural transformation between the two things and you request this to be in equivalence. So this is really a condition that with the given laxness constraint, this becomes the C bimodule map, CC bimodule map. Okay, and so that's the first thing. And the second condition is that C is dualizable. And this is actually equivalent. This is one of the first things to show. So under the assumption that one holds, and say replace 2 by 2 prime, and 2 prime is there exists the co-unit C2 spectra for delta. But this delta makes C into a want to be co-algebra, but you can co-multiply, but it's not necessarily co-unital. So I'm requesting that this has a co-unit. Right, and some of the co-units, I mean, of course, it's uniquely determined as usual, like because in co-algebras, co-units are uniquely determined. And so you can sort of, I mean, this is kind of part of that theorem. If you only have 1 and 2, then you get this co-unit. And you will see that this co-unit in practice will be the lower Schrieg functor. So part of the magic here is that the lower Schrieg functors drop out of just having this categorical properties. And of course, vice versa, if you just give yourself this, it's actually not so hard to prove that this is dualizable, because then you can just, I mean, this is like what's called Frobenius algebra. I'm going to write this down in a second. And then you can just write down the evaluation and co-evaluation of the self-duality. We make C self-dual. Okay, so this is like the notion of locally rigid, and then C is called rigid. Maybe I put it in this box. Rigid if also 1 is compact, tensor unit is compact. Right, so the distinction between locally rigid and rigid is just whether or not the tensor unit is compact. Okay, and now I'm going to give you a bunch of examples of this locally rigid stuff. So the first example is if just R is a commutative ring or ring spectrum.
So, Thomas, if you want to do the lower Schrieg in general, are you going to introduce a relative notion?
Yes, I want to. Yes, this is yeah. Maxime is right. So what I sort of said is, I'm going to give you the example, but in principle I know only that the lower Schrieg down to point, and of course you can do it more generally. Yes, I will talk about relative motion. Okay, so anyway, so R is a commutative ring. Then the claim is that mod R is rigid. With the usual tensor product over R. And of course, I mean, the unit is R itself, that's obviously compact. So what's the other thing we have to check? So we have to check, I mean, what is the multiplication? So the tensor product, the function from mod R, tensor mod R, to mod R, right? It's a tensor product over R. But what is this? This is the same as mod of R tensor R. Right? And so what is the tensor product under this? Then this is just induction along the multiplication of the ring itself, right? R tensor over sphere R to R is just a ring map, and so you can just use the induction. So what does this mean? So the right adjoint of that is going to be restriction along this multiplication map. And obviously a restriction preserves all colimits. Right? So that verifies condition, the first part of condition 1. And then secondly, also it's very obvious that restriction just commutes with tensoring from the outsides. But if you tensor with an R module from left or right, then restriction will just preserve this. So once you observe that this is like the way you can write down these functors, it's very immediate that this is locally rigid and in fact rigid. And you can make a somewhat more complicated example of this almost type. Where you do mod R comma I for R to R mod I, one of the homological APs in the commutative sense. And this inherits a tensor product coming from the tensor product of R. But you basically, I mean, these are like particular R modules, and you can just tensor them together over R. And the unit in here is I. And basically, this proof just goes through to prove that this is also locally rigid. Same version, you're basically tensoring over R, but sort of it's not rigid because the I might not be compact. So locally rigid. And it's rigid if I compact as an R module. But this might or might not be satisfied.
This
Usually not.
This is the case if and only if I is the sum of its R.
Ah, okay, so it might not be satisfied. All right. Yeah, I guess that's the example I had in mind to say it can happen, but didn't realize it was the only example. Okay, so
Sorry, what are the assumptions? R and I?
I mean, R to R mod I is a homological AP.
Because before you said for dualizable that every dualizable is like an almost category.
Yes. But here, I mean, everything is commutative, right? So you have a tensor product.
Oh, okay.
Right, so,
there
yes.
it wasn't.
Like, I mean, locally rigid is a notion for symmetric monoidal categories, whereas somehow the other one was a notion for dualizable ones.
Okay.
And for dualizables, you need those to be E1 rings, and here I need them to be E.
And is it also a kind of like, can you present all local divergence as being infinity almost?
I don't think so. Don't know for sure, but I don't think so.
No, because that would imply that it's simply generated.
I don't think so. No. All right. And I guess somehow maybe I should say one word about the name. So C is small, stable, and rigid in the classical sense. So what is the classical sense of rigid? Where does this name come from? Rigid usually is a notion for symmetric monoidal category where like every object has a dual within that symmetric monoidal category. Right? And so if this is the case, then in C is rigid. So in some sense, you can think of rigidity as just an extension of the usual notion of rigidity for small stable categories to this large world.
You can leave your
Yeah.
system.
Yes. Okay, so what about sheaves? That's kind of the example I wanted to talk about. And so let's do this a little bit more carefully. So if X is locally compact Hausdorff, then sheaves X is locally rigid. And if X is additionally compact, then sheaves is compact. Sheaves X is rigid. Right, so in general, I mean, I'm going to give you the proof, but let's just contemplate the difference between locally rigid and rigid for a second. So what does rigidity mean again? Rigidity means the unit is compact. What is the unit? The unit is just the sphere, the constant sphere, and mapping out of that is just global sections. Right, so in general, you're asking whether or not global sections preserves colimits, and of course, this is not true unless you're compact. Well, I guess, yeah, at least it follows if you're compact. If there's some stable sheaves, it's probably not an only if. But if they said it unstable, it would be compact also. Okay, now I guess why would that be locally rigid? So here again, we have to understand what the tensor product is. So the tensor product was from sheaves X, tensor sheaves X, to sheaves X. But what is that? That is just sheaves on X cross X. And I guess what is this tensor product functor? This is going to be given by pullback along the diagonal. Right, there's a diagonal map from X to X cross X. And the tensor product just ends up being pullback along the diagonal. So what is the right adjoint of that? That is then just pushed forward along the diagonal. But the diagonal for a locally compact Hausdorff space is just proper. Right, so this means this agrees with the lower shriek. But then you immediately see the lower shriek has a further adjoint with the upper star. That's why in this case this functor is strongly continuous. Did I say upper star? Sorry, upper shriek. Yes. Yes, this shows that this functor is strongly continuous. And how do we verify the Frobenius identity? Frobenius identity follows from proper base change along the following square. Bimodule, the fact that the right adjoint is a bimodule functor follows from proper base change.
It's literally just a projection. Yes, projection formula.
Yes, okay, so anyway, it's a projection formula. Okay, so maybe it follows from the projection formula.
It's also proper.
I mean, it is a fact that somehow you pull back along the diagonal and you can like first tensor from the outside, or like sort of do it the other way around. That's a difficult way. It's much better. And so you see immediately once you assume the six functor formalism and some properties of it, you immediately get that this guy is locally rigid. And let me just mention that necessarily the co-unit of this Frobenius algebra, so the map down to the unit, this will be the functor lower shriek from sheaves X down to spectra, where P is the map from X to the point. And why? I mean, this has to be the case because the co-multiplication is given by the lower shriek, and this just like by the fact that it's a functor, this makes it into a co-algebra with this co-unit. So it has to be this guy. Thing you necessarily will get out of the abstract machinery will also just have to be this one map. This is the lower shriek functor, or like, I guess you could call it complexly supported sections. Right, let me maybe write it as gamma. Okay, so this is these are the examples, and I guess there's more examples. One interesting example in my mind is also you take the derived categories to integers, the p-complete full subcategory. As a p-completed tensor product, and that's interesting because every object is dualizable. The only thing that fails here is somehow that the unit is not compact, right? Because the p-adic integers are not compact, because mapping out of it will not preserve filtered colimits. That's because filtered colimits in p-complete land are somewhat interestingly calculated. Okay, that's another example.
You said every object is reliably meant every compact object.
Yes. Every compact object, sorry, yeah. So it's compactly generated, yes, absolutely. So I should mention this category is in fact compactly generated. Nevertheless, it doesn't have the property that it's rigid, right? Because the unit is not compact. Sorry, and yeah, one proof is that every object is dualizable, every compact object, and so on. Of course, it can, I mean, basically never happen that every object is biolizable in these big categories. Thanks, Doc.
Zero bit.
Hmm?
What's zero?
Like Sasha is kind of the replacement for Ofer here. Okay, so what did I want to say? So if C is locally rigid, then I guess I was going to say that it has to do with Frobenius algebras. One way to say this is somehow without the co-unit. You can say you have the unit here, and here you can take the delta to go to C temper C, exhibits C as a Frobenius algebra. You know, there's a bunch of ways of saying what a Frobenius algebra are. And one way to say what a Frobenius algebra is, maybe the classical way, is you have a commutative algebra with a form from C to the tensor unit that is non-degenerate, that somehow exhibits it as being self-dual. Of course, you can just say the dual of that. It's a co-algebra with a co-form that exhibits it as being self-dual, and that's what we do here. And then once you have that, you somehow get a multiplication from abstract nonsense if you have such a co-algebra with a co-form, and then you see that this multiplication in fact has to be the multiplication you started with, and then you also get a unit. So the unit is then the co-unit, which is the dual of this map. Okay, so anyways, in particular, I mean, one of the things about Frobenius algebra, I think I said it in words verbally, is that the category C is canonically self-dual. It's equivalent to its dual. This is kind of one of the reasons that we care about these things. And in fact, I guess you can, I mean, we and I think some other people have thought about categorified notions of Frobenius algebra. So what you can say is like, a locally rigid category is the same as a Frobenius algebra in the ambient one category PRL. And then it comes with some extra structure, and the extra structure is that the multiplication is adjoint to the co-multiplication as a bimodule mesh. So you can sort of, I mean, make this notion, and I guess we call that, I mean, I call that a two Frobenius algebras. My two fellow script writers don't like that term, I think. Anyway, so this is a categorified notion of a Frobenius algebra, and you can do it, you can make it in every two category. And that's somehow what you get here. So you get all the benefits of having a Frobenius algebra. And one additional thing here, which I find very interesting, I mean, as I told you, in some sense the interesting thing is that we get the lower shriek to the point for free. Or whatever, not for free, but we get it. Abstract nonsense. And so this is the co-unit. And one can prove that the co-unit in this case is equivalent to the following thing. To the functor from C into spectra. So once I have a locally rigid category,
Sorry, what is the co-unit?
the co-unit is
Let's write it down.
I mean, the co-unit is the thing that exists a priori because we have a Frobenius algebra. It's a map from C to the unit. And so in my definition of locally rigid, I had this kind of 2' here, right? That's a co-unit for the co-multiplication delta. And a priori, I mean, you deduce it exists from abstract nonsense. I guess one way to say it is somehow once you know your self-dual, it's a dual of the map from 1 to C. Maybe if you want me to write down something, dual of 1 to C of the unit, right? So by the fact that C is canonically self-dual, we can do this. And so the claim is that this is always given by the following functor. You take compactly assembled maps out of the unit. Right, that's something you can always do if you have a dualizable category. You can take this kind of spectrums compactly assembled maps out of the unit. And that, I guess, this is also like what you, come on, in the chief case, this agrees with like compactly supported sections. And I guess the argument why this is always true, I learned from Maxim. That necessarily these axioms force the co-unit to be of this form. Okay, so This is what I wanted to say about this, and then you can somehow say a little bit more conceptually what the point is somehow. If you have your like locally rigid category, then I guess it's equivalent to its dual. You can write down the equivalent very explicitly. Right, the dual is left adjoint functors from C to spectra. And so what is the equivalence? The equivalence will send an object X to the functor which is compactly assembled maps from 1 into X tensor blank. And you see, like, if you are actually rigid, then this is just maps, right? Compactly assembled maps out of a compact object are the same as maps. And this is very useful because somehow you all of a sudden can classify all functors out of your category to spectra. And like, I guess you can also write down the converse functor. It will send F to, you have to do F tensor identity, right to delta of 1. Delta of 1 is an object in C tensor C, and then I apply the F tensor identity, so I get an object in spectra tensor C, so that's C. That's the inverse of that. So this is how from a functor you produce the object that it somehow in some sense represents in this sense. Okay, so this is very useful and
So the one here and the one there are different, right?
Yeah, this is spectra here.
Yeah, I guess this is spectra, so maybe yes. So yeah, this is, I mean, yeah. If you make this notion in ambient category, but thanks for finding it out. Yes, okay, so this is that stuff. And let me maybe spell this out in the case of sheaves, maybe on this board. Started. Let's see what happens here. So we get in particular, I told you that sheaves on a locally compact Hausdorff space is locally rigid. Right? So what I get from this is sheaves is equivalent to sheaves dual. What is sheaves dual? Sheaves dual is just functors, left adjoint functors from sheaves to spectra. So that's just co-sheaves. Right? Because I mean, sheaves is just generated by opens, so any such functor is determined on opens, and then it has to satisfy the co-sheaf condition. So we get from this that sheaves is equivalent to co-sheaves. And this equivalence is actually Verdier duality, Jacob's version of Verdier duality. So it's a non-trivial equivalence between sheaves and co-sheaves. For example, I guess, I mean, there's much ways of saying what it is. One way to articulate it is that the non-degenerate pairing, sheaves, tensor sheaves, to spectra, is just given by sending F tensor G, or F comma G, let me write like this, to compactly supported sections of F tensor G. That's just the pairing. If you spell out what happens, that's the pairing which is responsible for this equivalence. And I find this very nice that somehow Verdier duality or this equivalence drops out of this formalism. And I mean, whether or not, I mean, this is like a completely independent proof we can discuss. I mean, certainly not, because I included some fixed functor stuff, but I think it's still a very nice perspective. And
So can I ask a question about just an earlier point? So I was thinking the definition, the construction F tensor identity. What does that mean?
I mean, that's a functor from C tensor C to spectra tensor C. F is my functor, right? F tensor identity.
Delta. Sorry, the delta one is in C tensor C.
Yes, so I guess I can apply F tensor identity to this. And then I get an object in here which is C. Okay, so, and one thing I should say for y into x, and this is usually also like part of the Verdier duality statement, is that perhaps this map in LC house, then, I mean, the lower Schrieg functor is actually dual to the upper star functor. What does this mean? Once you know both categories are locally rigid, they're canonically self-dual. Right, the upper star is a functor from sheaves on X to sheaves on Y. You can just take the dual of that functor, right? I mean, in the category of dualizable categories, or I guess in the category of PRL, I should say, because it's not necessarily a strongly left adjoint functor. And then you get a functor from sheaves X dual to sheaves Y dual, and then you use somehow this like Vernier duality to identify both the sheaves, and then you get the Lower-Schrieg functor. So in some sense, you could construct this Lower-Schrieg functor just from upper star, together with the knowledge that both of your categories are locally rigid. Okay, so this is somehow how you can get the Lower-Schrieg from the upper stars. And as Maxime pointed out, I mean, I will in a second talk about a relative notion of that. I think all of this local rigidity is really a relative notion. And I will talk about that in a second. But let me first sort of give you some reason why it's useful categorically. And that's also due to the 7 authors which introduced the notion. If C is locally rigid, and M is a C module, in PRL. And then M is dualizable relative to C. So in other words, a dualizable object in the category of C modules. Right? The category of C modules inherits the tensor product. And you can sort of ask this relative dualizability if and only if M is dualizable. I guess this would mean relative to spectra, so in PRL stable. Well, that's very useful, yes?
Yes, maybe a question to this. Like, is then where this construction of the Schrieg functors, is there some interpretation for proper maps, F lower star being F lower Schrieg?
For proper maps, I guess, yeah, in that case you have to how to see that if I use this as a definition. Yeah, then I think one has to think about like this relative notion. And you know, I mean, for relative, yeah. I guess somehow, in some sense, you see the absolute case here, right? Like here we see once we're actually, this is the lower Schrieg to the point. Once we're compact, we somehow see, for example, from this formula that this is somehow true, and then I guess, I mean, as I said, I'll do a relative version in a second, and then you make a similar argument. I think all of this, by the way, is kind of nicely contained in Maxime's write-up. Yeah.
This proposition is still being true from Anima to spectrum.
Which proposition?
Your proposition about local rigidity.
Yes. I go from Anima.
C is spectra, and I say thanks to light on PRL.
Oh, sorry, that's a question.
So PRL sits before PRL stable?
Yes.
And you can ask who else to it.
No. I mean, I purposely only introduced this notion for stable categories. You can, I guess, come up with a notion of local rigidity for non-stable categories. Have to be a bit careful, but Anima will certainly not satisfy this. So, I mean, you know, there are examples like from additive land, like vector spaces, like that's the one category, it's certainly not stable, and this will be locally rigid, but certainly not Anima. And so, as an example of the last statement, we see that a Z-linear stable infinity category, formerly known as BG category, is dualizable over Z if and only if dualizable over S. Right, so in other words, I can choose evaluation and co-evaluation to be Z-linear and landing in the derived category of C as opposed to the sphere. And that's because mod Z is like locally rigid. Okay, and now I want to sort of give this a nice characterization of local rigidity and rigidity in terms of trace class morphisms. And I guess, yeah, for this end I have to talk about what trace class morphisms are. definition. And now I assume I fixed some symmetric monoidal infinity category C, and then a morphism in my symmetric monoidal category called trace class. Trace class if it lists as follows. So what is a morphism? So I assume my ambient category is closed symmetric monoidal for simplicity. It's not necessary for the definition, but it's easier to state and easier to comprehend, in my opinion. So this is the inner Hom. The morphism from the tensor unit into the inner Hom is the same as just the map from X to Y, or the universal property of the inner Hom. So this is my F. And then up here I have Hom from X, 1, tensor Y. Right, and by abstract nonsense, this will map to the inner Hom here. We all know this from vector spaces. It's like functionals, tensor Y, and so it's the canonical map up here. And so your request is to lift like this. Then it's called trace class. And of course, this is a very strong property for a morphism to lift like that. And I mean, as before with the compact maps, there's like a structure versus property thing going on. You can sort of say it lifts, or you can fix the lift, and that's a different thing. But yeah, I just care about the notion of admitting lift for the moment. And then you can use this to present, to give a characterization of rigidity. I think this I learned from Dustin, and I think local rigidity is due to Maxime in his, I don't know, like anyway, so it is a theorem, I hope.
You should also credit Peter Schulze.
Ah, okay, so. Okay, maybe, no, what's the alphabetical order Clausen? And that's this, C is the commutative alpha in PRL.
I also learned this from Dustin. I also learned this from Dustin. So.
Underlying dualizable. So if I already know that the underlying category is a dualizable stable infinity category, then you can say that C is locally rigid if and only if every compact morphism is trace class. Trace class. And so you can also say that the unit C is compact if with converse included holds. Trace class contained in compact. And then finally, of course, if you put the two together, you see that C is rigid if and only if we have equality. Compact equals trace class. And so you see this is like a nice local characterization or internal characterization of locally rigid categories. For example, you can give a proof that sheaves is locally rigid just by observing that the first holds. Right? Somehow in sheaves we've talked about somehow the fact that these inclusions.
Even generating correction.
Yes, yeah. Yeah, sorry. Wait.
You mean you want to show the generated collection of
Yes, so I wanna argue that in proving that sheaves is dualizable, we contemplated those morphisms where U somehow sits deep inside of V, meaning there's this compact which we can sandwich in between. And then basically you have to argue that those guys are also trace class, which is not super hard. You actually need a little less than, I mean, you just need that somehow, I guess the closure of U is still contained in V. Don't you need the compact sandwich in between, and then sort of you can argue that this is trace class. And I find this very nice that somehow This is not a hard argument once you have brought it down to this point, and then you see this very easy like observation eventually proves for you like variability, that somehow the category is self-dual. I find this a very nice like line of thought, even though whether or not I'm not letting it give you in the end. I'm just saying it's nice. Okay, cool.
So if I have some a point in map compared to a sample, can I get such a lift like in locally rigid space?
Wait, I mean I see. So the question was, let me repeat the question. The question was like, what's the notion between like I guess trace class being compact? This was kind of a notion for a morphism, and then you can ask what about the structures, and think they are also equivalent. Just somehow the spaces of such lifts are equivalent. So it's even a stronger statement than just the notions of being compact or trace class agree, but the spaces actually in fact agree in the rigid case. Or here you get
Look where you guess you just get that.
have a map from one to the other. Okay, cool. And so in the remaining minutes, I want to sort of do what I already announced, namely talk about the relative theory and how does this work. So point is that being locally rigid really is a relative notion in the following sense. I think this time I used the word relative notion correctly. So if I have A to B a map in the Alge PRL, then B is called locally rigid over A if first, I guess now I'm just going to write down everything the same way, just use the tensor product over A basically. So what I'm going to say is like, I have this multiplication B, and I'm asking this has a linear and co-continuous right adjoint delta B tensor AB. Right, so in particular the alinearity is important. There's actually alinear, and which is a bimodal map.
You could just say B tensor AB.
I think you also want the
What are you saying? Sorry.
Because of BB.
Which is a bimodal map. What? Sorry, I got a little confused. So several people throw in several improvements of this
I just
definition.
want to make a point that the two conditions are naturally combined.
Yes.
The statement that becomes B tensor AB linear.
Ah, yeah. Right.
the first condition also falls from the other one, so regardless of
you can just tensor over B tensor B. It's just all like the point is somehow once you have this adjoint, it's just you have for everything you basically have natural maps, and you just require some maps to be equivalent, right? And so this is why it doesn't really matter so much. I just wanted to make the point here, and that's kind of why I wrote it this way, that this map has to live in the A-linear world, right? The co-multiplication, and additionally it has to satisfy in the A-linear world the Frobenius identity. Okay, that's this, and second condition, I guess now is again that B is generalizable relative A, and that's again equivalent to the existence of a co-unit. And again, this is equivalent under the assumption that one holds. Right, so again, you could sort of say it's like a Frobenius algebra two Frobenius algebra, the way I sort of indicated this general notion in the category of A modules. Okay, so that's the relative notion. And I guess locally rigid, and then you could also say rigid if the unit also admits this adjoint. But I only introduce locally rigid for now. Okay, rigid again is just a statement that also the unit from A to B is internally left adjoint. So it's in the category of like co-continuous A-linear maps and adjoint. Okay, and here's the example. And that is if y to x is locally proper and separated, then map of topological spaces, then this sheaves of, if now I have to get the order right, so it goes from sheaves of y is a locally, sheaves of x, a locally rigid category over A, sheaves of x. Right, so in this case, neither of the two, unless y and x are locally compact Hausdorff, neither of the two are absolutely like locally rigid, but it's a relative notion here. And in fact, I guess, there's a bunch of ways of seeing that. For example, you can just copy the proof using 6 functors that I gave earlier for the fact that sheaves was locally rigid. But then, of course, you have to assume to begin with that you have this more general 6 functor formalism for these locally proper maps.
This Kunin property is something to check, yeah, that sheaves on the Plagal product over X is the same as the relative tensor product.
Yes.
Sheaves of Y is also
Yes.
sheaves of X.
Yes.
Is that easy or?
I think it's not so hard. You can basically reduce it to checking it for proper maps, in which case it's possible, yes. But you're absolutely right. So in some sense you can, in some sense you can say this Kunis property combined with 6 functor formalism always gives you like these kind of things.
Yeah.
And yes, you're absolutely right. So.
Usually Kunin is the hard part, at least in my
Yeah, but here somehow, for proper ones it's okay. And then, you can reduce to that case, like by descent essentially. Yes, good point. But, yes?
Is the form of the co-unit still sort of what you said before? You have this like explicit.
Yeah, I think it is this atomic style maps that Maxime comes up with. It's not, like the category is not absolutely dualizable. So I can't make sense of compactly assembled maps. But Maxime has this relative theory where you can make sense of atomic maps by means of some enriched assembly map. And then it should be that. But I haven't gone through the proof, to be honest. I think I just assume it works. Maxime, what did it? Probably. Everything seems sufficiently like categorical and like so that it should take over here, but I haven't checked it. Okay. Right. So
Thomas, maybe you wanted to say something about this, but like, is there a way to use this argument actually to produce the 6 functors? You cannot prove the statement without 6 functors.
yes, I think the statement can be proven without 6 functors. And so you see, it's only a property, right? So you don't have to produce the 6 functors. You just have to check like properties of certain things being equivalences. You can just do this. Like, in the end, if you stare at the definition, you just have to check that certain maps are equivalences, and you can just do that. And maybe I think there's probably also a very elegant way of doing that using a similar like characterization than that one. I haven't thought about this. What I have thought about is just checking it by writing down like the explicit maps and checking their equivalence. That can be done. And the proposition, of course, is is that if A to B is locally rigid, then M is dualizable. M is a B module, and B module M is dualizable over B if and only if it's dualizable over A. And more generally, in algebra, map B to C, then C is locally rigid relative to B if and only if locally rigid relative to A. But that's kind of the canonical analog of the statement that if your base is locally rigid, you can check stuff relative to that or to the absolute case. And so in our case, we see somehow, Maxim, did you want to say something?
I wanted to add something to the first one.
But yeah, let me maybe first finish this, like sort of, you see if we are in the setting where A is spectra, and we're in the setting of taking sheaves on locally compact Hausdorff spaces, you see somehow from this it immediately follows that sheaves of any Y is locally rigid relative to sheaves of X for any map between those. Right? Because both are absolutely like locally rigid. Somehow this is an inheritance property for local rigidity. And okay, Martin,
I just want to point out, the one also works for maps between realizable categories. Are going to be strongly like bilinear if only they're strongly alinear.
Ah, yeah, right. I think so. I
know that. I know that.
Yeah, okay. So it was not a question, but
a comment.
Yeah. Okay, not about the question. So Maxime remarked that it's actually in fact true that you can check like whether maps between realizable categories are like bilinear if and only if they are alinear. I know this for right adjoint.
They write that out. Yeah,
So if you have a left adjoint that is like bilinear, and you know the right adjoint is like alinear, then it's automatically also bilinear, with given to the standard constraints. Okay, so maybe I should also say, you know, like if B to C is locally rigid, you get this kind of unit map from C to B. And sort of if both are like locally rigid relative to A, you also get the unit maps like from C to A. And these indications of sheaves are these lower Schrieg functors, and you also have a statement that they compose in the obvious way. So you can somehow produce the lower Schrieg from C to B, and it will be compatible with the other lower Schriegs. So in fact, like what you can prove more generally, I mean, maybe I end it by this, is the following theorem.
So before that, I cannot read this second first of all, what?
An algebra map B to C, given an algebra map, maybe okay, so grammatically questionable, given an algebra map B to C, then C is locally rigid relative to B if it is locally rigid relative to A, right? So I have three algebra maps, A, B, C. Okay, and then I end somehow by saying that, I mean, the C-alg commutative algebras in PRL carries some sort of six-functor formalism with the exceptional maps these locally rigid. Maps. And the six-functor formalism will just send an object here to itself. Right, so six-functor formalism is a functor from some sort of geometric style category. The geometric style category is this category up, and it assigns a category, and of course it assigns a category which is itself. And then for a functor, it assigns the pullback, which is also itself. The point is, for those exceptional maps, you also have the lower Schriegs. These are now given by the units. And then you can check that this is in some sense some universal style six-functor formalism on this category. And I guess, I mean, I should say this is also, I mean, like, I think a student of Leo Neuhauser also has a proof of a version of this statement, which I should mention. And then the six-functor formalisms on, like, topological spaces, you can just get from mapping a topological space to the category of sheaves, any topological space. And then you check that somehow for these locally proper separated maps, the induced map is locally rigid. Maybe it's even true for locally proper. I checked it for actual separated maps, not locally separated.
So the locally separated one without locally rigid.
Ah.
But you can still make six.
Aha, okay. No, okay. So they're probably Kühne space, right? So.
No.
Okay. Anyways, okay. Thanks very much.